pair of reactions. What's been oxidized? What's lost electrons? Zinc has. Okay, so what's at the anode?
Zinc.
Which one would be like the anode reaction? Would it be 1 or 2?
1.
1, all right? Yeah, so this is our anode. And this means here, I mean, of course, by process of elimination, this would be the cathode. But here we've got chlorine that's been reduced, right? So you can figure that out with oxidation numbers, all right? So being able to, so if this was difficult for you, and I know that with everybody trying to study for exam 3, I know that it's very likely that some of this might have been difficult. Make sure that you go back and review oxidation numbers, right? You are going to need to be able to use your oxidation numbers to identify what's oxidized and reduced. Here, I actually split up the half reactions for you. In a lot of cases, and in some that we're going to see today, you're not going to have the half reactions split apart, and you have to actually write them yourself from the bigger reaction. So do go ahead, oxidation numbers, make sure you memorize those, and look back at your half reactions. So it's okay if that was difficult for you, that's fine. We just, now you know what you need to be focusing on for studying. Bless you. Okay. So what we're going to do now, where we're going from here, is we're going to take this idea of a voltaic cell, right, that we can harness now the movement of those electrons, that we can force them to move through a wire. We're going to actually talk about that in terms of force, all right? We are harnessing that for a specific goal. And I want you to think about this force that we're going to talk about, the force of electrons moving from one way to another. You can think about it as being analogous to like a waterfall. Has anybody here ever seen water flowing up a waterfall? Whoever said yes, no. No, you have not, okay? Water flows one way down a waterfall. If you're on Earth, I don't know what dimension you're in or what drugs you have taken. All right? Flows one way. From higher potential energy to lower potential energy, right? Okay? Force of gravity, right? Higher or lower. Okay. In that same way, just like water flows one way over a waterfall, electrons are going to flow one way when you're thinking about a voltaic cell. They're going to flow one way in a redox reaction. You're never going to have the flow of electrons reversed. They're going from a higher potential energy to a lower potential energy. If we were to set up a voltaic cell and compare it to a waterfall, we would see the anode, which is where the electrons are being produced. You can think of it that way, right? That's where something is losing electrons and you have electrons. Their movement now from the anode to the cathode is as spontaneous and unidirectional as water flowing over a waterfall. So those electrons are always flowing from high potential energy, where the anode is, to lower energy, where the cathode is. That flow of electrons goes one way. So what this means is, if I gave you a picture of this cell right here, and I didn't have where the electron flow was, you should be able to draw me a picture of the direction of the flow. It goes from anode to cathode, from production of electrons to where they are being used up. Okay? Now, in a particular cell, the difference between the potential at the anode and the cathode is called the electromotive force, or EMF if you want to be fancy. The name for that difference between the anode and cathode is called the EMF. Now, if we want to, say it, and this is the way that I'll say it most of the time, is not EMF. We usually talk about it in terms of cell potential. Again, because it's the potential energy available in that cell. If you want to give it, a fancy name, fancy variable, we just call it E cell. E cell is that potential energy difference between anode and cathode. And a lot of what we're going to do for the rest of the class time that we have is working with E cell in various scenarios. Okay. All right, so E cell is measured in volts here. So a volt, get in there. You got like a voltmeter, right, or voltage, right? You've heard people talk about voltage or different things. That's just what they're referring to, all right? Now, the cell potential that we measure in volts, it's dependent on a couple of different things. All right, so E cell depends on the reactions that you have. If you have different reactions at your anode and cathode, you can change the cell potential. So we have to consider when we're looking at this what kind of reactions occur. It depends the concentration, right? Our concentrations at our anode and our cathode are going to make a difference. Here, initially, we're going to get to some more complicated situations in a little bit, but right now we're going to talk about cells under standard conditions. All right, so standard conditions, remember that little, if you remember that from like, delta H and delta G, anytime you see that little circle, that means that we've got standard. So standard conditions mean that everything is at a concentration of 1 molar. All right, that's our standard conditions. We'll change that up in a little bit. It also depends, our E cell also depends on temperature. Now in this class, and all the examples that we're going to do, we are going to assume that our temperature is 25 degrees Celsius unless I tell you otherwise. But pretty much it's going to be 25 degrees Celsius. Okay? Just know that the change in temperature could have an effect because temperature can affect our reactions. All right? Now a couple of other things I want to say about E cell, right? It depends. If we're having our standard E cell, our standard cell potential, all of our concentrations are 1 molar. Our temperature is 25 degrees Celsius. And if we're dealing with gaseous reactants, what do you think the pressure is? 1 atmosphere, right? So pressure is 1 atmosphere. Okay. Anytime you see standard cell potential, that's what that means. Okay. All right. Now, like I said before, the most pertinent one of these categories, at least to start with, is the fact that cell potential depends on the identity of the reactions that's happening at the anode and at the cathode. Now, if we look at all of the possible reactions that we could have, we can actually measure standard reduction potentials. We can actually measure standards for any reaction that we would like to throw into one of our voltaic cells. And these standard reduction potentials we call E-red. Again, we've got that little, mark up there that tells us that that's at standard conditions. All right? So note here, I'm saying E-red, I'm not talking about E-ox. We're never measuring like oxidation potentials, standard oxidation potentials, only standard reduction potentials are we measuring here. All right? Now, and I'm not going to ask you about this in detail, just so you know, but I just want you to be aware that when scientists are measuring those standards, they compare them to something called a standard hydrogen electrode, which by definition, it's 0. So anything, any change in the voltage would be assigned to the other reaction. So just know that that's how they calculate it. You don't need to do anything fancy with that. Okay? All right. So it's just an example of this, one of our hydrogen electrodes here, where anything, here this is defined as 0. So any voltage that we would have moving through it would be assigned to the other reaction. Okay. Now I want you to note, this is an oxidation reaction, but we're still assigning a reduction potential to it. We'll see how we deal with that in just a minute. So what's the whole purpose of me talking about all this? If you have some voltaic cell and you are interested in figuring out what the cell potential is, you can do so by looking at your table of standard reduction potentials. And all you have to do, like what it says up here on the board, you find your reduction potential for your cathode. What's happening at the cathode? Reduction. All right, so you find your standard reduction potential for what's happening at the cathode, for the reaction at the cathode, and then you find your standard reduction potential for what's happening at the anode. What is happening at the anode?
Oxidation.
Oxidation, right? So this is why we are subtracting it instead of adding it, right? Because what's actually happening is the opposite. So you can remember it that way. All right. So what I would like you to do, and if you look in your book, you actually get a lot of good practice with, you can calculate E-red from E-cell and vice versa. We'll do a quick practice today with trying to calculate E-cell. So I'm going to have you guys try to calculate the standard cell potential. So what I'm going to do is give you a reaction, and this is similar to what you might see on a test, or what you might see if you get into 241 and you have to do this. I will give you a reaction, and it's not going to be divided into half reactions. Your task is going to be figuring out what's oxidized and reduced to help you divide it into half reactions. Once you've got that, I'll put this table back up. And I think everything that's needed should be on this table. Yeah. So I'll put this table back up. If you have this, up on your PowerPoint, you can look at that. And then I want you to use what we just talked about here. That E cell is E red cathode minus E red anode to calculate your overall standard cell potential. Okay, we're looking for E cell. So here is your equation, and we're going to actually use this equation again in another problem that we've got coming up shortly. All right, so go ahead, try this one on your own. Again, remember, divide it up into those half reactions. Figure out what's at the anode and what's at the cathode, and then you can